forecasting model. I'm Mark Ahlstrom, President of the Board of UVIG, the Utility Variable Generation Integration Group. UVIG is the leading source of global expertise for wind and solar operations and power system integration. And we really try to bring together people and solve technical issues in a safe place where we can talk about this and help people come to best practices and share lessons learned. Part of that is that we try to have a monthly webinar, which is what we're doing here today. Just want to point out we try to do this every month. These are free and open webinars. We encourage you to sign up and share the information with others. Our webinar coming up on March 27th will be from Derek Stenlick of GE, talking about storage value streams. So please keep our future webinars in mind as well. The other thing that we do is convene some very popular meetings where we get together face-to-face, and we have some great panel sessions and working group meetings on a wide variety of these topics. Our next major technical meeting is actually coming up on March 13 to 15 in Tucson, Arizona. And if you're an owner and operator of actual wind and solar plants, I encourage you to also check out the Operations and Maintenance User Group meeting, which is coming up in Chicago on March 27 to 30th. Information on all of these events and webinars can be found at the uvig.org website. For today, we have a very, very interesting discussion here where we're trying to look at some of the challenges of improving wind forecasting, which is obviously vital to the economic and reliable integration of higher levels of wind energy on the grid. So we're going to be hearing from the Southwest Power Pool first to kind of set the groundwork of what they're observing in today's forecasts. And then we'll hear from NOAA research about the latest findings from a new DOE-funded forecasting improvement project, where some of the new results are now available, and we'll be hearing about those in some detail. Because of the number of attendees, the attendees are muted, but there is a Q&A box, a question and answer area in the bottom right of your screen. So you can go ahead and type in questions at any time. I will be monitoring that and moderate any answers we need from the presenters, and to the extent we have time at the end, we will go through a Q&A with them as part of the webinar. If we get short of time and there's still their questions, we will try to have the speakers get answers to you that we will send out after the webinar, along with the copy of the presentations. And we are recording the event, and we'll send you a link to the entire recording as well. So with that, let me introduce our speakers. We're going to start out by hearing from Gunnar Shafer, who is an engineer at the Southwest Power Pool Operations Market Forensics Group. He joined SPP in 2016 after completing his master's in renewable energy with a specialization in energy storage from Universität Oldenburg in Germany. Before moving to SPP, he worked at the United Nations in Geneva, Switzerland on the West African Power Pool. And he's currently working on wind and solar forecasting accuracy improvements, as well as design for integration of utility-scale storage into the SPP system. His greatest love is traveling and using engineering to break down his cultural barriers, and he's lived in 4 countries and visited 27. Following up from that, Stan Benjamin, Dr. Stan Benjamin from the NOAA Earth Systems Research Lab will go into the research side of the meteorology improvements. Stan received a PhD in meteorology from Penn State, and he's the senior scientist for advanced system modeling at the NOAA Earth Systems Research Lab Global Systems Division. Stan has led with other scientists development of short-range operational weather forecasting models for NOAA, including the high-res rapid refresh that he'll be telling us about today, as well as the rapid refresh and REC models that are cornerstones of all the weather guidance used for aviation, energy, severe storm prediction, hydrology, and of course a major input for wind forecasting as well. So with that, Gunnar, why don't you go ahead and tell us about the situation in SPP?
Okay, can you hear me well?
Yes.
Okay, sounds good. Do I have control, or do you have control of the slides?
No, Ryan will advance them for you. Thanks.
There we go. Okay, so as you said, my name is Gunnar. Okay, I have the permission. There we go. Okay, so as you said, my name is Gunnar Shafer, and I'm honored to speak to UVIG today. We'll talk about some of the challenges that, as an RTO ISO, we have at SPP in the wind forecasting and ramping challenges. So here are some examples that we see within the wind arena in terms of the challenges that we face. So right now, SDP just crossed over the 18 gigawatt mark of wind, and these issues that we're seeing increase in magnitude, even if our error in the overall forecast is reducing. So these are the three main examples that we see. We see low-level jets, and you've probably been aware of this before or heard of it in other UVIGs. And they are when the atmosphere changes can be very quickly, dropping a low-level jet or a higher-level jet that has higher wind speeds, and it drops to a lower level. But it can also rise very quickly when the sun comes out in the mornings. So we haven't had any major instances in 2018 yet, but we did have one in December 2017. It produced a 3 gigawatt error in the forecast, and the wind rose 7 gigawatts in 2 hours, which is quite extreme. It was pushing our record of 3,500 megawatts in an hour, and it did it twice in a row in 2 hours. And the next, it should actually be 2.0, a low-level jet that we really see in sunrise, sunset, and I don't know if it would be necessarily called the low-level jet, as it's more to do with just typical boundary layer issues that arise when the sun comes up and the convection changes in the atmosphere. We had one just a couple weeks ago, a month ago, on January 15th, and the error was 2 gigawatts. We saw a wind drop of 2.5 gigawatts in 2 hours, and we also saw one that was pretty major or another example that I'll show later on was in November 2016, around the same magnitudes. The third challenge that we have at SPP is forecasting icing. So we haven't had any major icing instances in 2018 yet, but we did have one big one in 2017 and a huge one in 2015 where we lost quite a bit of wind, and it caused the day-ahead forecast to be off up to 6 gigs. So as we're talking about this, the wind forecasting error rate of SPP, the blue is day ahead, the orange is the midterm, and the grayish white is the short term. As the forecast improvements have been added over the years, and we've had some model training, the forecast accuracy has went down, but as I said before, the magnitude of the errors keeps growing. Okay, so the Sdp phenomenon that I sort of briefly already explained happens within our footprint that covers up to 14 states, and the phenomenon happens when the power tends to drop, the power production from the wind tends to drop in the morning between 7 and 11 a.m., and it sometimes can be very sharp, well off of the day-ahead forecast. We see it in spring, winter, and fall, and it's more of a problem then than the summer. In the summer we have more capacity ready to go due to the high load. At the moment, this has not caused many problems for the summer, as we're able to take care of it, but as the capacity goes and the magnitude grows, if we have a high wind day and a high load day, we could also see some major problems. Okay. So a low-level jet and the atmospheric stability, which maybe Stan will talk a little bit more about, and how the NOAA model can help. So when the surface air cools or heats up the Great Plains in the morning, when the sun rises, it pushes the low-level jet upward because of the convection, and so then therefore the wind power output drops quite rapidly within about an hour, and we see this most mornings, especially if there's high wind. Of course, the magnitude will be quite large. Then after, we see it at the sunset also. So when the low-level jet drops, because the sun is going below the horizon, the wind speeds will pick up because the jet's dropping. The events are triggered by a high-pressure system a lot of times that we'll see over the SPP, the middle of the U.S. If we're talking about the boundary label, yeah, stabilizes the power production as it's increasing for the wind. And the numerical weather models do not predict such events very well, and that's one of the issues that we have. We're satisfied with the product from Energy and Meteor Systems in Germany, but prediction on the smaller scale, the rapid refresh could possibly help us to provide alerts. Here's an example. This is the red chart is showing the actual wind output from SDP wind farms, and the blue is showing the wind forecast from the day ahead. And you can see that the wind went from 8 gigs to almost 16, which was our record on December 15th of last year. And on the record day, we happen to have another record of the ramp forecast and the error. So you see that the day-ahead forecast was quite off. We have shorter-term models. We have a short-term, mid-term, long-term. The short-term is every 5 minutes. It refreshes every 5 minutes for 4 hours out. But we can't show those due to some non-disclosure agreements. So it wasn't that bad in real time, but it showed some of the significant ramping issues. Here's the example of the sunrise sunset that we see in SPP. So the red is wind, the blue is the day-ahead forecast, and you see that around, what is that, just after 8 a.m. when the sun's really getting up and the convection starts, the wind immediately drops off. You have a little bit of an uptick in the noon hour when the atmosphere sort of stabilizes, and then when the sun goes back down, you see it pick up quite rapidly. And you can already see on the right side of the graph, that's the next day, and the same exact events happening the next day also. This is another really good example where you see the W form. We started calling it the bat formation. That's from 2016. The SPP wind resource forecast, you can see on the left side, the black line is the SPP wind, and then those are different studies that the wind forecast then goes into. And this shows the reliability of concerns that we have with where the wind can drop off faster than the forecasted model. The blue is the day ahead, so it's way off the day ahead forecast. And you see our structs and rucks weren't able to forecast the ramp problem. So one of our concerns and interests at SPP is looking at the different boundary layers within the wind and measuring possible wind speeds at different heights. This is an example from Germany that I had showing that the wind speed varies greatly with the height. And right now we have a majority of our 9,500 turbines in the footprint are 80 meters. And so we do have wind information from 80 meters, and we do have some from some met towers, but they're also at, their anemometers are also at 80 meters. And so it may necessitate in the future to have better forecasting of the ramping issues, to have a better idea of the boundary layers and the different wind speeds at different heights. Here's an example of the icing issues that we see. So the day-ahead forecast did not predict the icing very well. Even though you can see in the middle of the graph there was a sharp manual correction, so that was someone in Germany actually changing the forecast from the day-ahead manually, but it was still nowhere close. And that happened from the 15th through the 17th, so it was quite a long period. And the error was 4 gigawatts. Here's an image of the number of impacted resources from the icing event last year. There were 80 impacted resources. There were significant forecasting errors in most of those. And that's a nice image. You can see that the CROW outages, which is where members will submit outages for their wind turbines, did increase, but a lot of the icing was still unexpected, and so they didn't get the outages in time to get into the market system. Here's another icing example that we have from 2015. It was one of our more significant ones. There was 6 gigawatt difference in the day-ahead forecast back in November. You can see that even the 4-hour forecast, which would be more probably relevant to the rapid refresh from NOAA, it was still had significant error there of 1, 2, 3, 4 gigs. And one more icing example. the 6 gigs. So what are the next steps that SDP is going to take to enhance reliability, knowing these concerns are becoming ever more challenging, let's say? So we want to implement, and we already have in some instances, implemented a alerting system for these conditions so that we're not sideswiped by a major effect of the power dropping. Point 2, so get a list of the potential commitments that SDP will run additional sensitivities, intraday RUCs, reliability unit commitments, and structs around 6 or 7 a.m. if we think that we could see the conditions for a large ramping issue within the wind. And the operators have the ability to use these confidence bands that are produced by Energy and Meteor Systems in their studies. So that's available now. And additional thoughts from Energy and Meteor Systems. So one of the issues that we've had in terms of working with them was making sure that our data was accurate, our static data, especially on the turbines. And so we switched to a individual turbine-specific forecast in November. And then November actually proved to be our best forecasted month that we've had so far. But Germany said that this daily pattern will only increase as the hub heights get larger, and this problem is not going to go away anytime soon. Even if our footprint is widespread and the overall forecasting error is sort of distributed over a large area, there will still be a problem. So that's all from my side.
Okay.
Do you have a question?
Thanks, Gunnar. While we're switching it over to Stan here now, could you just elaborate a little bit for people that are not as familiar with, with system operations about why these deviations from the day-ahead forecast are a concern for grid operations? And I think you're hitting on a little bit by doing these additional commitments during the day where you adjust, which units are running at which levels, but why is this sort of deviation from day-ahead forecast a big concern?
Yeah, so we have day-ahead. Let's start with, we send data, static data to NM. They produce the forecast, and the forecast is then submitted to SPP, and SPP submits it out to the individual market participants in the wind farms. So then they can use these forecasts for their own day-ahead market bidding strategies. So if the forecast is off when they go into the market and bid in the day-ahead market, then you see these compounding effects that show up in real time. And that's sort of where the biggest risk factor is that they're expecting it in the day-ahead forecast, because a lot of wind farms don't have their own forecasts, so they rely on us passing E&Ms to them to make their day-ahead commitments. And that's really where it shows up in real time, is when the day-ahead is off.
So it affects all the other generators in the system as well, and then you might not have all of the resources that you want up and running because of some unexpected error, and that could potentially create a real-time issue or reliability issue as well, right?
Yeah.
Okay.
So even if the wind is different and it's forecasted properly in one area, if the whole day-ahead process is messed up by a forecast that's way off, it will financially affect all the generators.
So it's both an economic concern that it makes the system run less efficiently, and it's a physical concern in terms of which units are scheduled to run and so forth. Okay.
And in real time, you need more expensive products, ancillary service products. So that's the main. Right. Okay, I'm finished.
Thank you, Gunnar. Stan, why don't you go ahead and talk about some of the great research? Thank you.
Thank you, Mark. Are you able to see my screen okay?
Yes, looks good.
Great, okay. So thanks for the opportunity to talk. Thanks to UVIG, and also Gunnar, thanks for priming the pump here with some of the things that you've been seeing recently at SPP. We at NOAA in our research lab have been working with a strong group of people to try to improve the wind and solar forecast. Focus a little more on the wind here, but it's a three-dimensional atmosphere. We're trying to address all these needs, including what's taking place in the boundary layers. So outline here just quickly, we want to talk about what's taking place with our efforts, and you'll see some of that, including this recent complex terrain exercise that NOAA with the Department of Energy have been working on the Pacific Northwest. Take a look a little bit at some of the upgrade components that are coming in with the HRRR model this May for NOAA, including a 36-hour extension. Take a look a little bit more closely at this case study that including what Gunnar just pointed out from an event from just a month ago here. Talk ahead about the changes, a little more detail in the HRRR and the RAP, but then looking ahead even 2 years from now. So the outline at the bottom is going to tell you where we're at in this talk here. So first of all, again, what we're doing with the RAP and the HRRR, we're doing this hourly updating. We're bringing in observations here from lots of different sources, and we're bringing that information in to improve the initial conditions for the model. Those initial conditions are really kind of a combination of the observations from lots of different sources here, along with the previous 1-hour forecast. So we're always trying to correct that 1-hour forecast error from the recent observations. The HRRR is down at 3 kilometers. We're able to resolve circulations even within thunderstorms and have a better idea of how thunderstorms evolve. But sometimes that's pretty important for winter storms, certainly for different kinds of wind events that are affected by the lower surface. So the users of the HRRR really kind of started out with aviation and the evolution of the last 10, 11 years of the HRRR model. There was a great need to have better strategic planning for the HRRR, also for severe weather forecasting. But then a few years after that, it became apparent that we had the same issues with renewable energy for generation forecast there. There was a need that was identified in all these areas about day 2 outlooks from severe weather, also from the community that you guys on the phone now represent. There's sort of a general forecasting application that takes place from the HRRR, and then also looking at heavy precipitation forecasts for hydrology and flooding and so on takes place. So all these areas are areas that we've been developing the HRRR and the RAP model. So we really are working for you guys on the phone, along with several other key communities, different commercial and safety activities in the United States. Just to tell you what you already know, we understand these things, and the wind and the solar forecast, the accurate forecasts are needed. It's critical for you all, and so we understand that. So our processes in doing that have been trying to improve the understanding of these processes with clouds and turbulence in the boundary layer. Really the same processes are tied up together both for wind and solar forecasting, trying to improve how we address these processes in the model, and then also how we use observations to improve the initial conditions of the model and use every kind of observation possible. So we have a group of people, this is not all, but a lot of them here, that are working in our laboratory on renewable energy aspects, and they've all been connected with this recent wind forecast improvement project too, out in the Pacific Northwest, looking at effects in complex terrain. But it's really been paying off also across the whole country, and thanks again to Department of Energy as well as NOAA for participating in this project. So we do have an upgrade that's coming in with the RAP and the HRRR, this hourly updating forecast model coming up in 3 months. And so in this forecast improvement, we're going to be adding a few things, actually maybe not so much for this audience, but adding a HRRR model to run over Alaska. Aviation is so critical for transportation there that having this improved aviation forecasting is critical. But all of these forecasts are going to be extended out to a day 2 component, out to 36 hours. So it's going to be more accurate, it's going to run out longer, and then the Alaska domain are added to that. This is one of our verifications that we look at 10-meter wind speed accuracy. So the HRRR that's running now at NSEP at 10 meters, it's had a certain level of accuracy, not bad, and actually running up to 18 hours. But what we have with the new version of the HRRR model is that we have a more accurate forecast, and it runs out further, all the way out to 36 hours. And then comparing the HRRR at 3 kilometers versus the RAP at 13, the RAP covers a bigger domain, so that's still important, but we're able to provide improved 10-meter wind forecast, and we think also up at 80 meters at hub height. They're both going to be longer forecasts with this update. An example of the 36-hour forecast, and again, we know you guys are not doing flood forecasting, but it is an example here of being able to capture extreme weather events of all different kinds, including precipitation, and this is looking here at this precipitation of over 20 some inches of rain over a 36-hour period, with the new HRRR running back in August as Hurricane Harvey came on shore. So pretty good, you know, county level forecast here in these super intense precipitation rates. This is a slide that Gunnar just showed a few minutes ago, and just wanted to call out again, this is our problem also to have the models to best represent this. So the red arrows here are pointing at these times in the daytime when, and let's see if I can get the cursor to show up there, but they're showing in the daytime when the winds are about closer to the same speed at all different levels there. But the red or the blue events there are showing that stable atmosphere during the night when we have these drastic differences between 10 meters and certainly going up to 80 and definitely up at 150 meters. And as Gunnar said, they become more pronounced as we get hub height going up higher and higher. So that's part of our problem, and we get that, and we're working on that a lot. So this is another one of Gunnar's examples here, just showing this interesting dropout event that occurs between the nighttime strong winds and then the daytime strong winds. And we have this kind of fallout, a ramp event that occurs at that time of day. So we've been looking at this. We've produced kind of a climatology of HRRR 1 hour forecast and comparing it with a few towers, including the Wind Technology Center in Colorado. This kind of dip right here is that same kind of drop off. So we have higher winds at night, and this is actually looking, the blue is the observed, the red is from the HRRR model, and actually slightly higher. But we have this same kind of drop-off showing up in the morning hours. So this is the stronger winds in the afternoon here from stronger mixing from aloft, and this is from the nighttime, sort of the low-level jet, and this is the gap in between. So the HRRR is capturing that to some extent there, and it's great to see, or helpful to see Gunnar and the industry pointing out that is a key issue here in this drop-off. As part of that, we do have this new wind solar technology. This is a little bit side story here, but all of you know this famous graphic below here from NREL from their average 80-meter wind speed. But we're producing a similar new kind of data set, but using this hourly data simulation, using the very latest data, using also advanced representations of the boundary layer. And so that actually is described in a couple recent articles by a couple of us here, including some information offshore with data sets that are available. So this is meant to be helping out the industry here. So we're going to look at this one case now from just a month ago here, and it's one of the cases in which there was this morning drop-off, and 15th of January here is Martin Luther King Jr. Day. It was a Monday, and we had this front coming through. And so we're going to take a look at that event. So this is sort of a geeky weather map here, but hopefully you guys see that there's a high pressure and pushing down colder air from the north here through the southern plain states and certainly through Wyoming here. So this is actually at 12Z. That would have been, you know, about morning time, coffee time that morning on that Monday. And then by the next morning, that front had blown through all the way down to southern tip of Texas here. So there was an interesting and large-scale frontal passage that occurred between the cold air mass coming in here. So what we were able to do here is to get some information from one of these government websites, or actually not websites, a field site here at Lamont, Oklahoma. And so they actually have a 60-meter tower, and so this is not too far from the SPP power area in western Oklahoma here. So these are some time series here, a little bit like what Gunnar was showing, but this is for this particular period, and there's sort of an increase. The observations are in black here. So this actually is showing a pickup in nighttime winds, southerly, southwesterly winds. And then, as it turns out, in this particular case, this is not a drop-off from the time of day, because this is actually the frontal passage that occurs here. And what we noticed was that there was this drop-off about, so this would be 9 in the morning, that occurred before that northerly flow behind the front came blasting through. So we looked here at the time series of the winds. It's not exactly the same level, but about the same here from the old version of the HRRR that's running at NCEP right now in red, with the new version of HRRR, the experimental version, in blue here. So seeing a little bit better result here in getting the southwesterly winds picking up a little bit earlier, a couple hours earlier with the new HRRR. So this is now some weather maps here, again, over that same period. This is starting from Sunday night here, so valid at 0Z. And what these differences are here, let's start with this one here. This is looking at winds at 80 meters here. So this is at 0Z, so dinner time, and then 2Z, maybe 8 o'clock, 7 o'clock in the evening with these southerlies picking up. So this is the low-level jet as the stable layer kicks in, and then having winds here up to 20 to 25 knots here in this case. And these plots up above here from the new version of the HRRR model, and what they're showing is with these warm colors here, an increase of the 80-meter wind from hour to hour. This is actually a forecast here from all the way back on Sunday morning, actually Saturday night, I guess, really, with midnight. And these are runs now are valid well out here, showing this increase of winds in the early part of the evening hours here. This is actually the truth in the forecast from the HRRR analysis later on. So this would have been at 3Z, so maybe 9 or 10 that evening. Now we're skipping ahead here and now looking at runs that are valid at 4Z, 6Z, and 8Z. So as we go through the night hours, so this would be about midnight here, showing this increase in the southwesterlies showing up here. And the increase in the winds really were kind of completed by 10, 11 that evening local time. But then what you can see also is this front starting to come through from above here. And these greens above showing a drop-off actually in the HRRR model, which also showed up in the observations before this front hit here. So it's kind of a local detail. It's not exactly the same as the daily variation that Gunnar showed, but a little bit similar. It's the kind of details we know that's part of our problem to improve that forecast. So I'm going to go one more hour out here. This is now looking at 9Z, 10Z, 11Z. So now we're looking at coming into toward dawn on Monday morning, and these are showing the location of the front, again from this run from midnight on Saturday night here with this longer extended HRRR forecast. And so what we're seeing is definitely the 80-meter wind forecasts are definitely strong, but there's a little bit of a light area, a light wind dropout ahead of that front here that is showing up. So this is actually now going back to the time series of the winds with this the southwesterly winds, then a drop off, and then coming back with the northerlies. And this is actually, these different colors now are showing different HRRR experimental forecasts that are initialized at different times. And you know that notice that some of these forecasts were able to capture this drop-off in winds before the actual front came through. And really the bottom line story here is that we're continuing to try to use the observations, and with some success, to get more and more accuracy from using the most recent forecast. So we're starting to capture that here, even though the longest range runs did not capture that quite so well. So moving on from our wind case to a little bit more details in the data assimilation, we use all these kinds of observations here to go into the map and the HRRR initial conditions. A lot of them are available hourly. Obviously, radar data is critical. We actually are able to use lightning data also, data from the surface, data from satellites, including the new GOES-16 satellite with information coming in from that now. So these are improvements that we have in this new version of the HRRR that's coming in 3 months. We're using new observations. We're using better ways of using the current observations, including how we build clouds. And we're also using the radar data in a way that reduces too much convection. And we knew there was an issue, and probably some of you in the audience here are aware of that, kind of a little bit excessive convection in the HRRR in the first 6 hours, resulting in too many sharp ramp forecasts. We think that is definitely improved, not just in the frequency, but in the actual location. We're bringing in different versions of the cloud physics. A lot of the team working on this area with renewable energy is trying to improve the boundary layer forecast. So that's been a key area of improvement also. We revised in the actual land surface how we represent the roughness in a more accurate way, and even how we capture wind gust as part of the HRRR output. So I'll show you a couple examples here. First of all, from the data simulation, a couple of us working in our group here did a recent article to try to look at what is the impact in these short-range forecasts from different kinds of observations. And so what we found, this result in lower level wind forecast was the following, that in the summer and spring and winter, in all those three areas, actually the commercial aircraft, which are doing ascent, descent soundings around many airports in the country, has been a really key improvement. So we did forecasts here, model runs over a 10-day period, and did a whole series of them, and we one by one withheld different kinds of observations. So these birthday candles here are showing how much the forecast actually got worse as we got rid of those observations. But we also see the importance of the surface observations from near the ground. This is largely the 10-meter winds, and that is especially important in summer and spring, less so in winter. But having these kinds of experiments are really important for us to make sure we're doing the right thing and using observations in the best way possible. So we actually are able to do a cloud analysis. Also, we bring in observations from the satellite, also from the radar, and also from the surface observations, which have these LiDAR ceilometers that look up toward vertically pointing, and they are able to see clouds from underneath. So we bring in all this information into cloud information that then updates the cloud fields in the RAP and the HRRR. And this is an example here. This is an example actually I showed a year ago in another UVIG webinar, but this is looking at a cloud field here, looking at the cloud tops, and these colder colors means that they're kind of low-level clouds. But what actually happens is what shows in the left here. This is actually the change in using these different cloud observations from the ceilometer and the satellites and so on to make changes to a previous forecast, and that's how we're able to get the best possible initial conditions. So that's kind of unique work taking place in the United States with these short-range models. In the same way with the 80-meter winds, this is actually looking at a case again from a year ago here, and this is actually our initial conditions for 80-meter winds from the model forecast. But here is what the result was in bringing in the observations and trying to improve that 1-hour forecast, and showing actually in these green areas that the HRRR forecast was a little bit too strong, and just to be able to bring that down a little bit with the forecast. And now to show you the same thing, this is actually a case that I just pulled off from, I guess this would have been Monday morning of this week here. And so this is our 80-meter wind forecast. Now with actually some of the improvements from our energy team bringing that in. And so this is actually looking at the change in the analysis for 9Z on early Monday morning. Do the same thing with radar data. So this is actually looking at a typical kind of radar representation from the HRRR model and having these changes from using the latest satellite and radar information. So looking at the gaps here that we've had, we have had this issue in the past that the HRRR wasn't going out to day ahead. Well, that's changing. This is actually probably our biggest story for you all here. 36-hour forecast to be running every 6 hours, not every hour, but every 6 hours in the NOAA operational HRRR starting in May. Too many convective outflows, we definitely think that's better. We're looking ahead toward further improvements in the next version of the HRRR. Too much wind at night, down at 10 meters anyway, and we think there are some improvements here, but ongoing work in that area, and also an issue with inadequate clouds and some good progress in that, again, from the people working on our team here at NOAA. On the model itself, some of that is coming from these improvements in the clouds and the boundary layer. And just to focus on the boundary layer here, this is actually just a view in the Columbia Gorge. And so we're trying to represent these processes, the mixing that takes place actually at any location, but certainly in the Columbia Gorge with the complex terrain here, and how we represent the clouds. So we're trying to improve, in fact, having success in having how we represent this turbulence here. And there's sort of a local kind of turbulence, and sometimes these deep plumes that occur, and having improved treatments of these representations in the model. And it's sort of a big issue globally and the people here working at NOAA have been on the forefront of that and working with the international community for the short-range forecast. What takes place in the exchanges from the surface, having improvement treatments of that as well within the clouds and representing even clouds that are below the scale of 3 kilometers. And also people in our community are working on wind farm parameterizations, which are not yet accounted in the HRRR, but they will be in the very near future. Just an example here of looking at how we represent these small-scale clouds. This is, satellite image here, and having these small clouds. What we're going to do here is just a quick toggling back and forth. Look in the state of Alabama here, for instance, and so we just get more of these small clouds starting to be showing up here in the how much radiation reaches the ground, and that actually is a big part of our problem in having real good progress taking place in that. We have colleagues here in the lab who are working on having better solar radiation observations, so we've been using that as part of our model evaluation, and we've been looking at how we are improving both in the bias forecast for downward shortwave as well as the kind of the specific local nature, and we're seeing some improvements showing up there. And I know that this is kind of a wind seminar here, but the wind and how we represent the clouds are all tied up together in the boundary layer, and so as we improve one, we improve the other also. We measure also the progress in the model against weather balloons, which are launched everywhere, and what we see in the history over the last 5 years as we go toward the green is that we're getting less and less error, which means more and more skill, and in particular down near the surface here, this is actually showing an improvement in the lower troposphere winds near the surface that are taking place in the RAP and HRRR forecasts as we go through each year. On wind gusts, we just want to mention this briefly, but it's kind of an interesting case, maybe not for energy, but it probably was for energy. This is actually the night in which the Sonoma County fires occurred here. And what we found is when we looked at our wind energy fields that our 80-meter winds were maxing up to 60 knots here north of San Francisco, but our wind gust was less than that. We knew there was some issue with that, and out of that we were able to figure out a bug to that, and now having a representation that is better than what we had before of the wind gust. And we think actually that's an important field for the industry to consider also for when we get close to a drop-off kind of speed for possible damage. Just one other case here, an icing case here, a very unusual one that occurred just 6 weeks ago with ice and snow occurring down into Georgia and even ice into Florida here. This is a really tough case. These things don't happen except for once every few decades. And so we had our colleagues in Jacksonville tell us there was an excellent forecast, but because of the HRRR forecast for snow and ice accumulation, and this is actually coming from the HRRR forecast, these little red areas here are showing where the 36-hour HRRR forecast saying we're going to have some ice here with some heavy snow behind it going into this area. This is a very accurate forecast, and in the context of your icing from Gunnar's talk, I wanted to bring this up. We actually have a new field coming out now also with total freezing rain. This is actually a run just from this morning. I just pulled off the web here showing areas of freezing rain, and I saw Alain Forcion from Hydro-Quebec is online here, so probably he's already aware of these possibilities for some icing in southeastern Canada. We continue to look also a lot at the convection and seeing improvements between HRRR, the new version of the HRRR and the old version, and this is actually a case from last May here showing an improvement in the forecasts of severe convection outflows coming from that. I'm going to skip over that, just better winds here. We have further improvements coming up for 2 years from now and another upgrade from the HRRR, including use of information from fire and smoke. This is an example that we've been doing experiments with that, and we're able to get information about fires from different satellites that are going overhead and initialize an actual plume and existence of smoke and actually their emission from these different fire locations. This is going to be important also for solar and even boundary layer and winds overall. We're moving to actually having an ensemble of the forecast also by 2020, be able to have an ensemble with different representations updated every hour. That's going to improve our data assimilation and our forecasts overall. We put in code also to regularly represent for when they happen in the future, eclipses like this one that is taking place here. So we were able to demonstrate this in real time to be able to capture this. Obviously, it made a big difference for those few hours when the eclipse was going over. So we have these improvements coming up. Next to last slide here, I think, on the data simulation, the model, and we're addressing these different gaps for variable generation. And this is the last slide here. This is sort of the improvements that are coming up, implementing at NCEP. And then we have another version that will be coming in 2020 here. And then looking for anybody from our NOAA colleagues here, looking further ahead toward a unification of the dynamic core in the model. So welcome questions for Gunnar and me as you see fit, Mark. Thanks very much.
Thank you, Stan. This is very impressive. I mean, for many of you on the webinar who have been following this work for years, I think you'll be as impressed as I am that we're actually seeing this move into production quite quickly. So just to clarify, Stan, first of all, you said that what you were showing here as her research is actually going into production in May, including the 36-hour out runs, right?
That's correct, Mark. Thanks for calling that out. Yep, the 36-hour runs, these improvement that are coming out in part from the energy program.
And so that will be then available to be used in production purposes by wind forecasting vendors and others who want to take advantage of this. Very impressive.
That's exactly right.
Okay. Well, and an ensemble in 2020 is what you're shooting for as well. That would also be great. Okay. Stan, you also just pointed out the eclipse there briefly. We had a question about that, and also for you, Gunnar, in terms of what sort of effects did you actually observe in terms of wind ramps and potential wind plant changes from the solar eclipse in August?
From our end, actually, Gunnar, why don't you take it first, because you had, if you wish.
I had it on mute, sorry. I was going to pull up a presentation. I made a slide deck for the solar eclipse that I can share with Mark and then with UVIG that you can look at later, and it kind of goes into detail into what we saw in terms of solar and the wind. We actually saw the wind drop off. I don't know if that was because the cooling effects changed the boundary layers and possibly the stopping of convection changed some issues, but we did see the solar, and we accurately predicted exactly how much solar we would lose, and I think it was about half or so.
And we were able to see a drop off definitely of 8 to 10 knots, 4, 5, 6 meters per second from not having that mixing of the winds from aloft. So definitely a drop off showing there.
And on the eclipse, we saw several wind fronts. I think there was the one in Nebraska. There was some stuff going on in northern Kansas, Missouri, and something had just popped up in Panhandle, Texas. So it's very hard to make any correlation between why the wind did what the wind did. So I want to be clear on that.
Yeah, that's interesting, though, that, I mean, it is a factor that you have to take into account, that the solar issues, the radiation, the cloud cover, and so forth all have to be right in order to get these, especially these ramp forecasts of wind correct, right, Stan?
That's right. So the code is going to be in there. I guess the next big U.S. eclipse is in 2024, but we're going to be well ready for that. But really having code that can be applied in HRRR-like applications through the WRF community model for anywhere in the globe.
Excellent. Going back a little bit more to the use of these forecasts by power system operators, Gunnar, do you have a feel for whether you're more concerned about, under prediction or over prediction type situations? Are you more concerned when the wind, is not there and you expected it, or the other way around?
Not quite sure I understood that.
Well, I mean, we see some errors where the wind, you know, the wind drops off sooner than you thought, or it picks up sooner than you thought. You know,
okay.
Is one of those a larger issue? Yeah.
Yeah. So the larger issue is the wind dropping, all right, because we have to bring on conventional resources that need to have different startup times, quick start resources are more expensive, things like that. And if it's cold, the gas prices might be higher because the gas supply is being used more by the residential loads and commercial loads, heating things. So you can see some effects there. It's not as bad when the wind is ramping up. It's not a big of an issue because if we have problems, we can easily just curtail it. But when you're falling, it's sort of, you know, a falling knife. How can you catch it quick enough and without hurting the overall system?
Yeah, obviously your number one job is to make sure you have enough energy to serve your load, enough power at that instance. So you don't want to be caught short, right? So these cases where it falls off faster than predicted are your bigger concern, right? Okay.
Correct.
What about the issue about timing? I mean, are you in some of these cases, like you see here, you know, the forecast showed the timing pretty well, but it didn't get the magnitude. Are you also concerned, just as concerned about timing, or is it more important, you know, to understand the when or the how big, you know?
So we're trying to work with E&M on this as a model training issue because we don't want to change the entire wind forecast for these specific events. We just want the forecast to be a little bit more reactive for these specific instances, but we don't want the overall forecast. So we want it to be more manually adaptable so that we know that if we're starting to see a drop of maybe a couple hundred megawatts in the morning hour of 8 a.m. or 8:15 or whenever the sun's coming up, then we would like to be able to adapt our own forecast quicker, even in the day ahead. So if we see that it happened today and we see, let's say, a high pressure, there's no clouds, and the nighttime is also in that same type of weather, then we could also adapt the day ahead forecast for the next day, as you see in this example, that it happened again. And that we could use that, the day ahead forecast and sort of replicate it. And if we see that scenario happening, we can immediately switch over to this sort of sunrise sunset model.
Gunnar, please feel free to pass on our information here to E&M, and I know some of the other vendors are on here, so obviously we're trying to do this to benefit the vendors to provide better products for you guys.
Yeah, I know they use NOAA and they really like it, so we're looking forward to these enhancements. They're going to be huge, I think. So.
Yeah, both speakers have said we'll share PDF versions of these entire presentations with all of you. The other thing that you pointed out, of course, is that, Stan, you were showing the different model run times that through the day, you know, we get improved forecasts in general here as we get closer to real time. Right, and Gunnar, you also alluded, some people might not be familiar with the nomenclature about your intraday reliability unit commitment, where you're actually able to take advantage of improved models in addition to just the day ahead, but during the day, you know, 6 hours out, 12 hours out kind of stuff, where you can actually do some fine-tuning of how you're going to set up and operate the system with those as well. Is that correct?
Yes. For example, our day ahead models are updating periodically based on when E&M thinks that major changes might happen. So it's more of a manual type process where the short-term and mid-term are more of a, I guess, computer model, mathematical, don't change it that much. But even the day ahead where they can manually change things can go immediately straight into our operation studies, and we can see the outputs within minutes of any model changes or any unit commitment dispatch instructions that we need to make.
So the day ahead is obviously still very important, but are there certain, you know, time periods during the day? You know, how many hours ahead of real time is kind of when you can last use this information, or when it's most useful to you to do that fine tuning during the day? Are you talking like 6 hours ahead, or, you know, what sort of advanced?
Yeah, in that range, 4 to 6 hours should be.
Okay. So the ability to feed in real time.
Some really expensive last minute startup units, but
yeah.
Yeah.
Obviously, the more accurate you can be farther ahead, the better, but you can still use improved forecasts that come in during the day up to about 6 hours or so.
Yeah, definitely.
Okay. Okay. Great. There is a question here, a very good one from Scott. Thank you. We do have the UVIG forecasting workshop coming up in St. Paul in June. And the question is, could we expect a further update around, from both of you on this information about what's going on in your system and with your HRRR model potentially at that workshop? I'm certainly hoping we can. Are you guys up for giving an update for everybody in person at the forecasting workshop?
Yeah, sure. We definitely would like to participate in that. So we'll figure out one or more of us to participate. Thanks, Mark.
Yeah, that's a great event that we've been running quite a few years now, and we try to get all of the practitioners and users of the forecast together and look at the actual operational use of wind forecasting in the utility system operations, sense power system operations. So,
I can't make any commitments yet, but I'll try and see what I can do. Definitely can give an update. I don't know if it will be in present form or if I'll be there.
Yeah, we try to have E&M, all the forecast vendors participate. It's a great event where we get together and talk about this. With that, I want to thank both of you. I think we did a great job of covering a lot of information and the questions that came in here. I want to remind everybody that the upcoming events are the Spring Technical Meeting of UVIG is in Tucson on March 13 to 15. We then have the O&M user group for operators of wind and solar plants and increasingly for storage and other assets as well on March 27 to 30th in Chicago. We have a webinar on storage value streams, looking at battery storage, where that's going, from Derek Stanlick of GE on March 27th. You'll see an announcement coming to you by email on that. And we will be sending you links to the recording, copies of the presentations, and other information by email following up on this. So please thank the presenters here. I really appreciate it for a great job, and you'll be getting more information from us with the details. Thank you so much.
Thanks to the community for letting us participate in this. We look forward to hearing from you even more.
Thank you, Stan. Thank you, Gunnar.
Thanks.